right now, across the country, there are literally millions of dollars of incredibly capable, heavy-duty industrial machinery just sitting idle in scrapyards.
Yeah, it's a massive point of friction in heavy industry right now.
And the most frustrating part, it's not because the core machinery is broken, like the steel is solid, the mechanics are sound,
Right.
but the engine powering the whole setup is just, you know, a few years out of environmental regulatory compliance. We're looking at a reality where an entire piece of indestructible equipment is essentially condemned just because of a single compliance sticker.
Oh, absolutely.
Yeah.
The waste is staggering. I mean, both economically and materially. You have these massive capital investments being tossed aside because the regulatory landscape just moves faster than the equipment's actual lifespan.
Well, welcome to the deep dive, because today, for you listening, we have a mission to explore an engineering workaround to that exact problem.
And it's a pretty clever one, too.
It really is. We've got a technical brochure from Hitachi Global Air Power US detailing a highly specific piece of equipment. It's their Sullair certified glider program.
Yeah, covering their portable lubricated rotary screw air compressors.
Exactly. Models like the 375H, the 375H HAF, the 425H, and the 425H AF.
To anyone outside the industry, that just sounds like a catalog of alphabet soup. I mean, it's a lot of
Oh,
numbers.
totally.
But what this brochure actually outlines is essentially an industrial heart transplant.
An industrial heart transplant. That's a great way to look at it.
Right.
Our goal today is to go beyond these spec sheets and understand the mechanical realities of what they're actually doing here.
Right, because the glider concept isn't just about casually swapping out parts.
No, not at all. Okay, let's unpack this for you. Imagine taking the reliable, indestructible chassis of your favorite vintage truck and dropping a brand new, modern, emissions-compliant engine right into it. That's essentially what we are looking at here.
What's fascinating here is the deliberate philosophy behind it. In a glider program, you take a brand new replacement engine, in this case a John Deere, with a 2-year or 3,000-hour warranty,
Right.
and you pair it with a remanufactured Sullair air end. And then everything else finishing out the package, like all the surrounding components, are brand new.
Okay, wait, I have to stop you and push back on the terminology right out of the gate here.
Sure.
When you hear the word remanufactured, the immediate assumption is that you're buying something used, like patched up and given a fresh coat of paint.
Yeah, that's a fair point.
So for a contractor staking their livelihood on a job site, why on earth would they want a remanufactured core component in a machine that is otherwise brand new?
Well, that skepticism is entirely valid,
Right.
especially if you compare it to, like, consumer electronics.
Yeah.
But a rotary screw air end is not a delicate circuit board.
No, it's huge.
It is a massive block of precision machined metal. When they talk about the legendary Sullair air end in this brochure, they aren't just marketing. They're referring to a piece of engineering that is structurally overbuilt.
So when it gets remanufactured, they aren't just cleaning it.
Not at all. They're taking those massive metal housings and the helical rotors inside and actually remachining them back to their exact original factory tolerances.
Right. Let's actually talk about how that mechanism works, because I think that explains why the metal is worth saving. A rotary screw compressor basically acts like two massive interlocking meat grinders.
That's a great visual.
I have these two helical screws that spin against each other, taking in a large volume of air and forcing it down an increasingly tight funnel. The mechanical stress of squeezing that air is immense.
Precisely. And the tolerances between those two spinning rotors are microscopic. Yeah. So if the original cast iron housing and the rotors are fundamentally sound, remachining those surfaces and replacing the bearings gives you a mechanism that is mechanically indistinguishable from one that just rolled off the assembly line.
Which is wild.
It is. And by keeping that core proven air end and dropping a new Tier 3 emissions-compliant John Deere engine next to it, Hitachi Global Air Power US basically bridges the gap.
They solve that scrapyard problem we talked about at the beginning.
Exactly. They give contractors the legacy hardware they trust, wrapped in a compliant package, though, you do always have to check state and regional regulations, as the brochure specifically notes.
Right, of course. But it fundamentally redefines the life cycle of heavy machinery. So let's look at the actual power plant driving this whole setup.
Let's do it.
The engine doing the heavy lifting here is a John Deere 445HF 285. It's a 4-cylinder engine putting out 140 horsepower.
Or 104 kilowatts.
Right, with a rated speed of 2,200 RPM.
And we should really look at the physical geometry of that power generation. The bore and stroke on this engine is 4.19 by 5.0 inches.
A 5-inch stroke is significant. For you listening, a longer piston stroke generally translates directly into low-end torque.
Oh, absolutely.
But what stands out to me isn't just the torque, it's the thermal reality of running an engine like this. The spec sheet lists a 4-gallon cooling system and a 9-quart engine oil capacity. That is a massive volume of fluid for a 4-cylinder engine.
It really is. And it tells a very specific story about thermal stress. I mean, think about how a typical truck engine operates.
Right, you accelerate, you coast.
Exactly. You stop at a light. The RPMs constantly fluctuate, which gives the engine moments of relatively low stress to cool down.
Sure.
This John Deere engine doesn't get that luxury. It is designed to hit 2,200 RPM and stay there under full, unyielding load for hours on end.
Wow. Just sitting there screaming at 2,200 RPM.
Yeah. The thermodynamic heat generated by that kind of sustained combustion is brutal. You need those 4 gallons of coolant and over 2 gallons of oil just to absorb and carry that heat away from the engine block before the metal fatigues.
Which brings up the fuel consumption, and this is where I think we see a brilliant piece of engineering psychology.
Oh, I love this part.
Right. So the brochure lists a 56-gallon fuel tank. At full load, the engine burns 6.55 gallons per hour. So if you divide that out, you get roughly 8.5 hours of continuous runtime at maximum capacity.
And that is absolutely not a coincidence.
Now, it perfectly matches a standard heavy-duty workday. 8.5 hours aligns right up with the exhaustion limit of a human worker.
Exactly. You fuel the machine in the morning, fire it up, and it runs nonstop until the crew clocks out. You never have to kill the pressure, shut down the tools, and refuel in the middle of a job.
It's workflow efficiency dictated purely by a fluid capacity spec. It's so smart.
If we connect this to the bigger picture, all of this engineering points to sustained reliability. But, sustained reliability means nothing if the machine can't wake up in the morning.
Good point.
Let's look at the electrical system. It's a standard 12-volt system, but the battery rating is 1,100 cold cranking amps, or CCA.
Wait, 1,100. That is a violent amount of electrical power for a startup.
It is. But it's absolutely necessary when you understand the environments these machines live in. Imagine a job site in the dead of winter, well below freezing.
Okay.
Diesel fuel physically changes in those temperatures. The paraffin wax in it actually begins to gel.
Right.
At the same time, those 9 quarts of engine oil we just talked about turn into a thick, resistive sludge.
So it's fighting itself.
Yes. To get a high-compression diesel engine to turn over when it's essentially glued together by cold oil, you need a massive, immediate surge of torque from the starter motor.
An 1,100 CCA guarantees that starter motor has the electrical violence required to break that inertia. Okay, so the power plant is a tank. It manages its own heat, it aligns with human work shifts, and it can wake up in a freeze. But torque and horsepower don't clear debris out of a mining hole.
No, they don't.
We need to talk about how this machine physically translates rotational engine power into raw, usable air pressure. Because looking at the delivery specs, the output here is immense.
This is where we get into the different model variations and where the engineering trade-offs become really clear.
Right.
You have the H models, so the 375H and 425H, which deliver 375 and 425 cubic feet of air per minute, respectively, at a rated pressure of 150 psi.
Okay, that's already a lot of air.
It is. But then you have the 375 HHA model, which pushes an incredibly dense 200 psi.
200 CSI. And the plumbing reflects that. The standard models have two 34-inch service valves. But the 375 HHAF swaps those out for a single massive 112-inch valve.
Yeah, that's a huge difference.
You just don't use a valve that thick unless you're moving serious, dangerous amounts of energy. But here's a specification that I really struggle to wrap my head around. The maximum operating altitude for these compressors is listed at 10,000 feet.
Right.
I mean, think about how winded you get just hiking at 10,000 feet. This machine is still up in the clouds, pulling in thin air and compressing it to 200 psi. That is some serious lung capacity. How does it do that?
It is an incredible thermodynamic challenge, and it all comes down to volumetric efficiency.
Okay.
At 10,000 feet, atmospheric pressure drops significantly. The air is physically less dense. The oxygen molecules are literally spread further apart.
Right.
So when those interlocking rotary screws we talked about earlier open up to pull in a breath of air, they're pulling in a much lower mass of air than they would at sea level.
So to maintain that 200 psi output, the compressor essentially has to work twice as hard to squeeze that thin air down?
Exactly. And when you compress a gas, you generate heat.
Yep.
When you have to compress a highly expanded, thin gas into an extremely tight space to hit 200 psi, The thermal spike is exponential. The risk of thermal runaway inside that compressor casing is massive.
Which perfectly explains another spec that jumped out at me. The compressor oil capacity is 7 gallons.
Ah, yes.
We talked about 9 quarts for the engine, but the compressor itself requires 7 full gallons of oil. I have to assume that is not just for lubrication.
You're spot on. In a lubricated rotary screw compressor, the oil serves 3 distinct critical functions.
Okay.
First, yes, it prevents the massive metal screws from grinding against each other, but second, it acts as a fluid seal.
A fluid seal?
Yeah. Because the air at 10,000 feet is so thin, it wants to slip backward through the microscopic gaps between the rotors. The oil fills those gaps, sealing the pressure in.
Wow, that's ingenious.
And third, to your point about heat, those 7 gallons act as a massive thermal sponge. The oil absorbs the violent heat of compression and carries it away to a cooler, preventing the air end from literally welding itself together.
It's fascinating how interconnected every single fluid and dimension is. And looking at the model lineup, you can see how they are catering to entirely different industrial psychologies.
How do you mean?
Well, if you're a contractor running a bank of pneumatic jackhammers on a highway project, you don't care about extreme pressure. You care about sheer volume. You want that 425H model so you have enough cubic feet per minute to keep all those hammers firing simultaneously.
Right, but switch the scenario. Imagine you're doing deep hole abrasive blasting, or like drilling into bedrock high up in a mountain pass.
Okay.
Volume isn't your primary problem there. Resistance is. You need intense, unyielding pressure to force abrasive material through a hose or to clear heavy rock dust out of a deep vertical shaft.
Right, so that operator is entirely reliant on the 200 psi capability of the 375H AJF model.
Exactly. It's about matching the thermodynamic profile of the machine to the physical resistance of the job site.
But that brings up a massive logistical hurdle. The brochure calls these portable air compressors.
Yes, portable.
But when you tally up all this heavy iron, the engine block, the remanufactured cast iron air end, the 56 gallons of diesel, the 4 gallons of coolant, the 9 quarts of engine oil, and the 7 gallons of compressor oil, the working wet weight of this machine is 4,440 pounds.
It is over 2 tons of metal and fluid, and physically it takes up a lot of space. The dry weight alone is 4,050 pounds.
And the dimensions.
It's over 156 inches long, 77.2 inches wide, and 74 inches high.
So we are talking about a box that is roughly 13 feet long, 6.5 feet wide, and over 6 feet tall. That's practically the weight of a rhinoceros.
It really is.
Now, the spec sheet casually mentions a maximum towing speed of 55 miles per hour. I look at those dimensions and that 4,400-pound weight, and I see a massive towing hazard.
Yeah, you have a very top-heavy piece of equipment.
Filled with over 60 gallons of sloshing fluids. Dragging that down a highway at 55 miles per hour seems incredibly dangerous. How does the design actually support that dynamic load?
This raises an important question, and it's why the engineering of the trailer is just as critical as the engine itself. It isn't just about static weight. It's about dynamic stress. The manufacturer addresses this by significantly overbuilding the axle.
Oh, really?
Yeah. The working weight is 4,440 pounds, but the axle rating is 5,000 pounds.
So they build in over 500 pounds of structural buffer.
Yes. And that buffer isn't really for the highway. When a contractor pulls this off the pavement and onto a rutted, uneven job site, the trailer frame is going to twist.
Oh, sure. One tire drops into a ditch.
Exactly. One tire might drop into a trench while the other is on solid ground, sending a massive shock wave of torque directly into the axle. That 5,000-pound rating ensures the axle won't snap under the dynamic twisting load of an off-road environment.
That makes perfect sense.
Furthermore, they specify 200 2575D15 tires. Those aren't your standard passenger car tires. They have rigid sidewalls explicitly designed to fight the lateral sway induced by a high center of gravity and those sloshing internal fluids.
So they are managing the kinetic energy of the machine before it ever even gets turned on.
Precisely.
Speaking of getting turned on, there's one final engineering hurdle here that I think often gets overlooked.
What's that?
We've established that inside this 13-foot metal box, we have a 4-cylinder diesel engine running relentlessly at 2,200 RPM, chained to 2 massive metal screws violently squeezing thin air down to 200 psi.
Right.
The mechanical violence happening inside that enclosure is immense, yet for the 375H HAF model, the sound level is listed at just 76 dBA.
which is a remarkable achievement in acoustic engineering.
To put 76 dBA in context for you listening, that is roughly the volume of a standard vacuum cleaner. Or,
Yeah.
like standing on a sidewalk next to a busy road, it's definitely loud, but it isn't deafening.
Right.
How do you trap that much mechanical noise inside a metal box without simultaneously trapping all the heat we just talked about?
That is the internal paradox of compressor design. To trap noise, you need a sealed box covered in thick, heavy acoustic dampening material. But to reject heat, you need massive airflow. If you seal the box too tight, the engine and the compressor suffocate and overheat in minutes.
So how do they balance it?
The enclosure on this glider is basically a highly engineered wind tunnel. The acoustic baffling is shaped to force the incoming cooling air to navigate a labyrinth of turns.
The labyrinths.
Yeah. Sound waves travel in straight lines, so every time the sound hits a corner in that baffling, the acoustic foam absorbs the energy. By the time the air exhausts out of the machine, the thermal energy escapes, but the acoustic energy has been trapped and absorbed by the enclosure.
Wow, so it isn't just a protective metal shell, it's a functional muffler for the entire system.
Exactly.
It really aligns with Sullair's slogan printed in the brochure, always air, always there. They engineered this 2-ton block of iron to sit on a job site, run all day, and not physically torture the crew working next to it.
It demonstrates a holistic approach to industrial design. They aren't just solving for pressure and volume. They are solving for the human realities of towing, temperature, and acoustics.
It fundamentally changes how you look at a piece of equipment parked on the side of the road.
It really does.
So let's take a quick step back and synthesize everything we've pulled from this single technical brochure. For you listening, we started with this idea of a disposable industrial culture where million-dollar machines are just scrapped over compliance issues.
Right.
But here, we found a 4,400-pound counter-argument. We found an engineering philosophy that takes a legendary, perfectly machined rotary air end, gives it a brand new, environmentally compliant 140-horsepower John Deere heart, and packages it in a chassis built to handle off-road torque and high-altitude thermodynamics.
It proves that innovation isn't always about creating something entirely unprecedented from scratch. Sometimes the most rigorous engineering goes into making two different generations of technology seamlessly cooperate.
I think that's the ultimate takeaway for you listening today. We obsess over the bleeding edge of technology in shiny presentations. But the real mechanical marvels, the machines that are physically altering our infrastructure, are often hiding in plain sight, buried in practical, hyper-specific spec sheets.
It leaves us with a provocative thought about the future of sustainability, really.
How so?
Well, in our rush to transition to entirely new green technologies, we have a dangerous habit of assuming that everything old must be discarded. But the Sullair glider model challenges that entire paradigm.
It does.
Is there a deeper, more profound wisdom in this hybrid approach? Merging the unyielding, mathematically proven durability of legendary remanufactured industrial parts with the precision of modern, compliant combustion might not just be a stopgap measure. It might actually be the most practical, resource-efficient blueprint we have for the next century of heavy industry.
It's a compelling argument against the scrapyard. I mean, why melt down the unbreakable iron when all it needs is a cleaner breath of air to keep working for another 20 years? It turns out true industrial progress isn't about discarding the past. It's about strategically remachining it for the future. Thanks for diving deep with us today.